Nice to meet you. I'm Myungjae Choi from Yonsei University in South Korea. Today my talk is about aerosol observations from the HIMAWARI, GOCI, and GEMS satellites over East Asia. First part is the introduction to HIMAWARI 8, GOCI, and GEMS. Today's talk will cover these three geostationary satellites for aerosols and air quality over East Asia. Left one is the HIMAWARI 8 full disk true color image. The HIMAWARI means a sunflower in Japanese. The second one is the GOCI image, and right one is the GEMS nitro dioxide image, which will be launched in next year. This chart shows the spatial and temporal resolution of air quality satellites. The spatial resolution is different according to the target product. The red triangle represents the trace gases sensor, such as ozone and nitrogen dioxide. The green squares represent the greenhouse gases sensors, such as carbon dioxide and methane. Generally, these gases measurement sensors have coarse spatial resolution as a few kilometers. The last one, the yellow circles represent the aerosol sensors, and they have higher spatial resolution, less than a kilometer. We can see that most low Earth orbit LEO sensors have a day to week temporal resolution, but geostationary orbit sensors have higher temporal resolution from a few minutes to 1 hour. In this talk, I will only cover aerosols using GOCI, AHI, HIMAWARI, and GEMS for air quality studies. The full name of GOCI is the Geostationary Ocean Color Imager. It was launched in 2010 and is still working well and will be ended in 2020. Its primary objective is the monitoring of ocean colors to understand ocean biology, such as the chlorophyll concentration and dissolved organic materials. There have been many ocean color sensors, such as CGCS, CWIPS, MERIS, MODIS, and recent OSEI. All of these ocean color sensors are LEO sensors. So GOCI is currently only one ocean color sensor in geostationary orbit. GOCI has 8 channels, 6 visible wavelength channels from 412 to 618 nanometer, and 2 near-infrared channels as 745 and 865 nanometer, like light under panels. Its temporal resolution is 1 hour, from 9 half to 16:30 local time. It covers East Asia area as light figures, including Eastern China, Korea, and Japan, and its spatial resolution is 500 meter by 500 meter, which is very high resolution despite of geostationary satellite. The second one is AHI. Its full name is an Advanced HIMAWARI Imager. The 2 satellites contain these sensors, HIMAWARI 8 and HIMAWARI 9, which is launched in 2014 and 2016 respectively. The primary objective of HIMAWARI 8, HIMAWARI 9 AHI sensors is the fast scanning and reporting of meteorological conditions over East Asia, such as typhoons or clouds. There were previous meteorological geostationary sensors over East Asia, such as MTSat by Japan, MI by Korea, or Fengyu number 2 series by China. But those had only one broad visible channel, so it is not suitable for high-quality aerosol retrievers. In these days, other similar next-generation meteorological satellite sensors are ready or already launched, like ABI operated by US, AMI will be launched in next year by Korea, or Fengyu 4A series operated by China. The temporal resolutions are different according to the measurement mode. The first, the focus mode over Japan area here has every 2.5 minutes measurement. The full disk mode covering East Asia and Oceania has every 10 minutes measurement. So for the full disk measurement, we can get totally 144 times per day. AHCI has 16 channels, 3 visible channels like 0.47, 0.51, and 0.64 micrometer. These 3 channels are related to aerosol cloud and some more, but we can use these channels information for aerosol retrievers. And it also has 1 near infrared channel and IR channel like 0.86 micrometer, and 2 shortwave IR channels like 1.6 and 2.3 micrometer. These channels can be used to get some surface reflectance information for aerosol retrievers. And it also have 10 infrared channels from 3.9 to 13.3 micrometer. These infrared channels are very useful to detect cloud information. The spatial resolution is different according to the channels, from 500 meter invisible and 1 kilometer invisible and 2 kilometer in infrared. Third one is the GEMS. Its full name is the Geostationary Environmental Monitoring Spectrometer Onboard GeoComSat 2B satellite. It will be launched in next year, and the lifespan is approximately 10 years. The primary objective is for air quality measurement, including aerosols and trace gases like ozone or nitrogen dioxide. Other similar previous current or planned sensors are SBUV, GOM, GOM2, SKIAMAKI, OMI, OMPS, TROPOMI, and all these sensors were and are on low Earth orbit also. So GEMS is the world's first geostationary air quality sensors for trace gases retrieval over East Asia in next year. But there are also other geostationary air quality satellite like Temper over East Asia, Temper over USA, and Sentinel-4 over the Europe. So this international constellation for observing air quality will be planned now. GEMS is also have a 1 hour temporal resolution during a daytime, so totally 8 times per day from 9 to 16 as local time. And we can see hourly NO2 retrieval result over East Asia like here. It has some coarse spatial resolution like 3.5 or 6 by 8 kilometer at Seoul for aerosols and trace gases respectively. and it also covered a broad area of East Asia. The latitude is from 5 south to 45 north, and longitude from 75 to 145 east. The spectral range and resolution is here, the 300 nanometer to 500 nanometer with 0.6 nanometers spectral resolution. It is very high resolution to detect trace gases absorption band like light under figures. Compared to the aerosol, the trace gases have a high frequency absorption band like ozone black line, NO2 like red line, or formaldehyde like a green line, or glyoxal like blue line. To detect this high frequency absorption band, we need a very high spectral resolution measurement. So GEMS is focused on that measurement. The second part is the aerosol optical properties and retrieval algorithm. This is the principles of aerosol remote sensing. We can see the sunlight is here, and it starts from the sun to Earth, and it also passes through the atmosphere and reflect from the Earth, and we can detect this reflected sunlight signals from the satellite here. The signals can be scattered from the atmosphere or Earth's surface, and we should distinguish these signals. The Rayleigh scattering shows symmetry distribution between forward and backward scattering. So this scattering characteristics is very well known. So we can get the Rayleigh scattering information from the calculation. But aerosols shows the misscattering characteristics. Misscattering is the very high forward scattering compared to the Rayleigh scattering. So this Rayleigh and aerosols have a different characteristics. So our goal to get the aerosol information is to distinguish this aerosol information only from the totally added signal in the sensor in the satellite. Here's the definition of aerosol optical properties. First one is the aerosol optical depth. Aerosol optical depth, or AOD, is the degree to which aerosols prevent the transmission of light by absorption or scattering of light. We can think easily like low AOD means the very clear condition in atmosphere, and high AOD case in very thick of aerosols in the atmosphere. This AOD value is total column integrated value from surface to top of atmosphere. So it is some different with the ground measured PM2.5 concentration due to the definition. If you want to get the PM2.5 or PM10 from the satellite, we should consider this definition difference according to the altitude. Second one is the Armstrong exponent. The Armstrong exponent is the spectral dependence of AOD, and it is related to the particle size. The high Armstrong exponent, about 2, means very small particle like smoke aerosols, and low Armstrong exponent close to 0 is the coarse particle like dust. Next definition is the fine mode fraction, FMF. This fine mode fraction is based on the aerosol volume size distribution. Generally, aerosol have the bimodal shape, like fine mode particle and coarse mode particle. And the phi mode fraction means the total phi mode AOD by total AOD. So its range is 0 to 1. And if there are coarse particle is dominant in atmosphere, that atmosphere should have the low phi mode fraction, and vice versa. The when phi particle is dominant, then it has the high phi mode fraction condition. The last one is the single scattering albedo. The single scattering albedo is the effectiveness of scattering related to extinction. So if light is if light meet the aerosol particle, then the light should scattered or absorbed. So that absorption coefficient plus scattering coefficient means the extinction. So single scattering albedo is defined the scattering coefficient by extinction coefficient. We can see these right figures. The observing particle shows low single scattering albedo like black carbon. It contains more light. So if there are so many observing particles there, the atmosphere is changed to warming atmosphere. Compared to the low single scattering albedo condition, in high SSA condition, particle is make some more scattered to the atmosphere, to the top of atmosphere. So it means that there are less energy in atmosphere, so it makes the atmosphere as cooler. Please note that there are no units for AUD, Ångström exponent, phi mode fraction, and single scattering albedo. This is the top of atmosphere reflectance component. This is based on the Honingen et al. In AMT paper in 2011. And the x-axis is the wavelength from 400 to 900 nanometer, and y-axis is the reflectance. And the black line is the top of atmosphere reflectance, which can be measured at the satellite. In the satellite measurement, we can see this totally integrated reflectance like a black line. But in real atmosphere, there are some combination of surface reflectance and Rayleigh reflectance and aerosol reflectance. First of all, this blue line means the Rayleigh scattering. The Rayleigh scattering changed here, but as I mentioned before, the Rayleigh scattering can be calculated very easily because we already know the characteristics of this Rayleigh scattering. But the difficult one is the green line, the surface reflectance. Surface reflectance can be changed according to the surface type, like desert or ocean or vegetation area. So if we get the more accurate aerosol signal, we should know the surface reflectance signal very well. If we know this surface signal and Rayleigh signal from the top of atmosphere, then we can calculate it aerosol signal only, like red line, as TOA reflectance minus surface reflectance minus Rayleigh scattering reflectance equal aerosol reflectance. So aerosol retrieval algorithm has this concept. This slide is same with the previous Pawan's presentation. This shows the simplified version of the remote sensing processes and more focus on the aerosols. It starts from the satellite measured spectral radiance, and it also required a priori information and radiative transfer theory. And it also required a retrieval algorithm, including cloud masking, surface signal determination. And using all of this information, our final goal is to get aerosol optical properties like aerosol optical depth, AUD, Armstrong exponent like particle size information, and SSA like sorptivity information from aerosols. If we get this information from the satellite, we can use this satellite information to the real air quality applications. Hereafter, I'm going to explain each step for aerosol retrieval briefly. The aerosol retrieval algorithm is applied to cloud-free and snow-free pixels over land and cloud-free and ice-free over ocean pixels. General characteristics of cloud compared to aerosols are different for visible and infrared wavelength channels. The clouds are spatially inhomogeneous and bright in visible wavelengths and low brightness temperature due to high altitude. So we can use this information to detect the cloud and mask out from the GOCI, GEMS, and AHI. Some specific channels are very sensitive to ice crystal or water droplet. So we also this information from the AHI because AHI has many IR channels compared to GOCI or GEMS. The snow or ice surface are too bright in visible wavelengths, so there are less aerosol sensitivity. Thus, most sensors cannot retrieve aerosol information over there. Meanwhile, the UV wavelengths still have some sensitivity for aerosols over desert, so GEMS can get aerosol over desert compared to GOCI or HIMAWARI. The right figure shows some example of the aerosol retriever. We can see bright surface and cloud pixels doesn't have any AUD pixels, but other pixels are retrieved as AUD from 0 to 2, like rainbow colors. First one was the cloud masking, and second part is the approximation of land surface reflectance. The first concept is the target concept based on the Kaufman et al. 1997 and Lemmer et al. 2005. The basic assumption is that over the surface, such as vegetation, the visible wavelength surface reflectance has a linear relationship with shortwave IR channels. Because shortwave IR channels like 2.1 micrometer have low sensitivity to aerosols, so we can get surface information well compared to information better compared to the visible wavelengths. This method can be applied at each measurement using measured visible and shortwave IR radians. And also this method considers different relationship according to the surface type, like NDVI, vegetation index. Currently, this target concept is applied to the MODIS target algorithm and Beer's aerosol algorithm now, and it also can be applied to AHI sensor because the AHI sensor have shortwave channels compared to GOCI and GEMS. The second concept is the minimum reflectance technique from composite database. This is the pre-calculation concept. We can think this is the climatological database. Each scene has cloud or aerosols, so it is hard to get surface reflectance directly. But if we combine each scene during a month and composite that data as one data, then we can get clear pixels to get surface signals. This method was and is applied to CWIPS and MODIS Deep Blue aerosol retrieval algorithm and Tom's and OMI aerosol retrieval algorithm, which is using the UV characteristics. So this method can be applied to GOCI, GEMS, and AHI out of sensors. This is one example of the land surface reflectance using the minimum reflectivity technique. We can see the aerosols and cloud signals at each scene, but we combine this each scene data for 1 month and same hourly scenes after the Rayleigh scattering is corrected. Then we can find some dark scene and consider it for surface reflectance like white figures. We can see most aerosols and clouds are masked, and we get the real surface signal from the composite database, but we also see the remaining bright pixels like snow here. So this part is for the aerosol optical properties. In real atmosphere, aerosols have very variable shapes and properties like left figures. Left figure shows some Sahara dust in US, smoldering phase smoke from Amazon, smoke cluster from Amazon here, and China pollution here. To calculate these optical properties using computer, aerosols should be considered more easily. Like right part, observing or scattering in terms of single scattering albedo and coarse or fine. It represents the aerosol size and the shape of aerosols like spherical or non-spherical. To retrieve aerosols from satellite, these simplified assumptions are required. This is the last part of the aerosol retrieval algorithm. As I showed before previous slide, we should simplify aerosol properties like size or absorptivity or particle shape. But we also should consider the particle distribution, like aerosol is where aerosol is located, upper or bottom layer of the atmosphere. So we can consider various available atmospheric conditions such as particle size, distribution, refractive index, and also the possible top of atmospheric reflectance or radiance can be calculated using the radiative transfer model. Like here, exact name is the 6SV Libratron or VLIDAR. This is the radiative transfer calculation program. Then we can get the calculated TOA reflectance using RTM here. And we also have the observed TOA reflectance, top of atmosphere reflectance from the satellite measurement. Then we can compare two top of atmosphere reflectance. The final step is the finding best condition which make least difference between them. Then we can get aerosol optical properties such as AOD. Then from now on, I will show some retrieval results from the geostationary satellite GOCI, AHI, and GEMS. And those products are based on our group's Yonsei University aerosol retrieval algorithm. Using the visible channels, it has the very high sensitivity for particle size. So the product is aerosol optical depth and size information like fine reflection and Armstrong exponent from GOCI and AHI. Those two products have the same spatial resolution, like 6 by 6 kilometer spatial resolution. And GOCI has the 1-hour temporal resolution, and AHI has the 10-minute temporal resolution. The bottom is the GEMS. GEMS measure the UV wavelengths. So UV wavelength has very high sensitivity for aerosol absorption. So GEMS aerosol product will provide the aerosol optical depth and single section albedo or UV aerosol index or aerosol layer height. It has 3.5 kilometer by 8 kilometer spatial resolution over the Seoul area, and it also has 1-hour temporal resolution. This is one example of the GOCI retrieval result. This is the very heavy dust case in April 27th in 2012. In the left upper figure, we can see very thick yellow dust is transported from the inland of China to Korean Peninsula. We can see this aerosol plume as a yellow color in RGB image. After the aerosol retrieval algorithm processes, we can get very high AUD above the 2 from GOCI and MI and MODIS. MI is the previous our meteorological sensor having one visible channels, but it has the very high frequency of the temporal resolution, like 15 minutes interval. So we can more smooth change of aerosol transportation from MI and 1-hour temporal resolution from the GOCI. But MODIS have the 2 times per day from the aqua and terra measurement, so there's only 2 scenes during a day. This aerosol plume shows very low fine motor fraction, like about 0.3. It means that coarse particle is dominant, and we can see this low fine motor fraction like a blue color here. And according to the aerosol type classification based on fine motor fraction and single scattering albedo, we can see the aerosol particles are classified like dust over here area. This is other case, smoke case in May 19th in 2016, measured from the AHI HIMAWARI aerosol HIMAWARI sensors. The main focus is over here on right upper area. Here you can see very high, white color aerosol plume is transported from the Russia to the Hokkaido in Japan area. Over here we can see 10-minute temporal resolution image from AHI. It's like an animation or movie. Because we assumed 2 different surface reflectance techniques, AHI has the 2 products, merged version, composite method, and dark target method, and both methods results shows a similar AUD about the 1 at the center of the plume. And MODIS, Terra, and Aqua also have to detect this plume, but due to the sunglint issue, there are so many no retrieval pixels around the Hokkaido area. And bears also detect this plume, but also has some no retrieval area due to the sunglint. Sunglint means that too bright ocean surface due to the geometry between Earth, Sun, and satellite. Most sunglint area of the geostationary satellite is located near the equator, so we can see more continuous image aerosol plume over the East Asia from China to Japan. And in this plume, in this case, the plume also shows very high fine refraction compared to the previous case. So It means that the smoke plume is very well classified in this algorithm. The last one is the dust case in March 31st in 2007 from the GEMS aerosol retrieval algorithm. Actually, currently we don't have the real GEMS measured data, so we use the OMI level 1B data to simulate to check our retrieval algorithm for GEMS. So we can see this result from the OMI, but we will expect the similar result from the GEMS. This dust case, we can see very heavy dust plume is transported from the inland of China, and yellow color in RGB image. And the aerosol type classification, it also detected as a dust particle very well, like a blue color in aerosol type map. The retrieved aerosol particle depth at 443 nanometer shows the up to the 3. It's very thick aerosol plume, and it also shows some single sector albedo like 0.88 to 0.94. It means that they observed properties like a dust. The main advantage of GEMS is that it can calculate the aerosol effective height using the UV sensitivity for aerosol loading height. The right under figure we can see here. The green color and red circles are obtained from the LiDAR measurement Calliope. And Calliope can use the laser information to get the aerosol height information. So in generally, we use this Calliope height as a reference. And for the red color is the GEMS aerosol retrieval result, and GEMS also detect this aerosol loading height very well. This aerosol loading height is very important to distinguish the relationship between total AUD from bottom to top of atmosphere and the surface measured PM2.5. This is some result of the validation of GOCI, AHI, and GEMS aerosol optical depth using AeroNet measurement. The AeroNet is the ground-based remote sensing network operated by NASA, and it has very high accuracy, about 0.01 for AUD. So it's generally reference data to evaluate the satellite data. For GOCI, AHI, and GEMS, the AOD shows very high correlation with the AeroNet AUD. The linear correlation coefficient is about 0.8 to 0.9. But there are still some assumptions and limitations of the aerosol retrieval algorithm. The aerosol retrieval from limited satellite measurement is an ill-posed problem. Actually, real atmospheric status is a combination of unknown variables, but satellite measures provide limited information. It means that amount of unknown information is greater than degree of freedom of satellite measurement. Thus, the a priori information and accurate radiative transfer theory and model are required to retrieve high-quality Earth information from satellites. To do this work, we required a very well-assumed aerosol particle distribution or representative aerosol types or particle shape, or we also required very well-known surface reflectance. or other atmospheric condition status also, like gas profiles or temperature profiles also. The next part is the practical uses of geostationary aerosol datasets and their application to air quality studies. Maybe most attendees want to know this practical use using geostationary satellite product. So I will show some results based on our research studies. To utilize geo-aerosol data practically, the accuracy should be validated using ground-based measurement. In this study, the GOCI AOD was validated using AeroNet ground-based remote sensing data and compared with other LEO sensors AOD products such as BEARS and MODIS. The upper figures is the AOD versus satellite product, each satellite product, and second bottom figure panels are the AOD errors according to the AeroNet AOD range. During 2012 to 2013 over East Asia, GOCI AOD shows less bias and matched better with AeroNet compared to other products like BEARS or MODIS. We can see the bias is from GOCI is about 0.02 or 0.05 compared to other higher bias here. So also it also shows a high frequency of within the expected error range, like 66% compared to other products. So we can start to use GOCI AOD data for air quality studies with the advantage of high temporal resolution and high accuracy also. Strength of geostationary orbital measurement. The detection of highly variable aerosol transportation. Aerosol can be very highly variable, especially heavy aerosol transportation cases. This is the case of May 2016. The smoke aerosol plume was transported from Russia to northern Japan, Hokkaido area. In the first day, the left figure, the AOD was about 0.2. For second day, the AOD was changed rapidly from 0.2 to 1.5. Rapid change during a day. The black dot line is the ground-based measurement of AeroNet, and we can think this AeroNet as the reference data. But lower orbit measurement like blue or green or magenta color, MODIS dark targeted blue, BEARS or MISR, it only detects once or twice times per day. So it is very hard to detect this rapid change of atmospheric conditions using the lower orbit data. But AHI and GOCI, the yellow and red dot follows and detect very well of this rapid change during a day. And at the image, the upper one is the GOCI and bottom one is the AHI. 1 hour and 10-minute temperature resolution differently. And we can see very heavy aerosol plume is transported to the Hokkaido area. And we can more smooth image from the AHI. These plumes are changed continuously but still located over Hokkaido area up to 4 days. After the plume was passing, AOD decreased to 0.5 and less at the final last days. Main advantage of geostationary satellite is to detect highly variable air quality status continuously. During the 2012 spring, there was several heavy aerosol events, such as dust cases in the first period, anthropogenic emission, and smoke cases as follows. In upper figure, original chemical transport model result are red line. We can see this red line here, and the ground-based PM10 measurement is the blue line. We can see big gap between observed blue line and no assimilated chemical transport model result like a red line, big gap between them. And GOCI can provide hourly AUD images, so it can be assimilated with chemical transport model multiple times during a daytime. Assimilation means that the integration of chemical transport model and satellite measurement together. In this study, we did a 3-hour interval assimilation for the GOCI, and also together with the MODIS 2 times per day. When the chemical transport model are assimilated with MODIS and GOCI, the result shows improved matches with ground observation like a black line. The assimilation result is the black line. We can see the change from red to black line is more close to the blue line. Compared to the MODIS only data assimilation, GOCI plus MODIS result shows less bias over all sides like green colors. It means that multiple times assimilation is very useful to improve the chemical transport model accuracy. This is another collaboration work with Dalhousie University. GOCI AUD is used to adjust geoscan air quality model result. Before the adjustment, the slope of linear regression line between model and ground-based measurement was about 0.5. But after the adjustment, the slope is changed to the 0.9, like a light figure. This study generates PM2.5 distribution with very high accuracy over Eastern China and each season. We can see the low PM2.5 during the spring and autumn season, and summer and autumn season, and very high PM2.5 during the winter season, December to February. This is another studies to the assimilation between GOCI and chemical transport model. CMAC AUD can also generate AUD and PM2.5, PM10 distribution like left figure, and GOCI can measure atmospheric conditions like here, second column. And the assimilation between them is the assimilation result is the right column, third columns in the left figures. There are so many techniques to integrate two chemical transport model and satellite measurements. The first one method is called the optimal interpolation method, and second one was the gap filling method to fill the empty data for model time and model time and cloud masked area. There is the typo 3. We can get the hourly GOCI AUD product over each hour and cloud-free area, but model generated no cloud area AUD also, cloud area AUD also. So to combine them, this gap filling method make a continuous AUD plume based on the statistical approaches. So this several integration development is used to the real air quality forecasting and assimilation studies in Korea. Not only for the air quality studies, this geostationary satellite can provide very high spatial resolution aerosol distribution over East Asia due to the many observation samples during a daytime and fixed observation area. It means that same pixels are measured continuously from the geostationary satellite measurement. This monthly AOD distribution is generated by using the GOCI AOD, and this spatial distribution is very well matched with MODIS and VIIR's recent result here. But this MODIS and VIIR's provide AOD monthly product as a very coarse spatial resolution, like 1 by 1 degree of latitude and longitude box. However, GOCI can provide climatological value as high spatial resolution, like original 6 by 6 kilometer level 2 resolution also. And we can see the general change of the AOD distribution according to the season and area. AOD can shows the peak at the May and June time and low in the winter time, but it is very different shape, different characteristics with the PM2.5, so we should know about it. The daily mean ARNet AOD can be calculated from the all point. All point means that several minute temporal resolution measurement, and daily mean AOD from GOCI is from 8 times measurement during a day, but only 1 or 2 times in MODIS is available. It means that more samples in GOCI can provide reasonable daily and monthly AOD, and this can be less affected by sampling issues for climatological analysis of aerosols. This time series is a monthly AOD time series using the AeroNet, MODIS, and GOCI over Beijing, Yonsei University over Seoul, Osaka in Japan, and Gwangju in Korea. We can see the linear regression coefficient R, or RMSE error, shows very high accuracy for the daily monthly AOD time series in GOCI compared to the dark target and deep blue MODIS product. Due to the multiple times measurement advantage, this geostationary satellite is hard to use as a primary satellite data to support air quality field campaign. This is main information of the COROS AQ campaign over Korean Peninsula and May to June in 2016. During this campaign, we also provide GOCI and HIMAWARI aerosol product from our university, and they are also MODIS, OMI, or other lower survey satellite products also. This satellite product can provide broad spatial coverage for key atmospheric components like aerosols, ozone, or precursors. And during this campaign, there are 3 aircraft measurements like NASA DCA, Langley King Air, or Hansa King Air. This airborne measurement can provide the real sample data of atmosphere. And simultaneously, there are several air quality models are learned, and this satellite data are used as a reference data to evaluate the several air quality models. This is the one example of during the COROS campaign. The bottom figure in left figure, bottom distribution of left figure is the GOCI AOD from 0.0 to 1.5. Red color means the very high AOD plume is transported from the China to Korea. And this hourly GOCI AOD can be matched with several times with during the air quality campaign during a day. And the vertical curtain plot is from the HSRL airborne LiDAR measurement. LiDAR can provide the vertical distribution of aerosol profiles. So combining these two products can, when we combine this horizontally spatial distribution of aerosols from GOCI and vertical properties from the LiDAR, then we can get the 3D aerosol distributions over the over the Yellow Sea in this campaign. And we can see this aerosol plume is transported from the China based on the backward trajectory modeling. So this combining geostationary satellite data is very useful to understand the real status of the atmosphere during a day. The last part is the additionally available air quality data sets from geostationary satellites over East Asia in the near future. This is the main information for the GeoComSat 2A and 2B, which is the next generation of geostationary satellite operated by Korea. GeoComSat 2A will have the AMI, the meteorological sensor. It's very similar like ABI in the previous presentation. So it will provide a full disk image as a 10-minute temporal resolution like HIMAWARI or Fengnyun Forces or ABI over the USA. We also, the Korean Space Agency also will have these sensors. So it will provide aerosol and optical depth and size information. And the GeoComSat 2B will have the GEMS, as I showed before, and GOCI 2. So GOCI 2 is the next generation of GOCI. Because GOCI 1 will be end in 2 years later, so this GOCI 2 will have a continuous law as followed to GOCI 1. So different wavelengths, different characteristics of the temporal resolution and spectral resolution provide different aerosol optical properties. So, and this is the not for the aerosols. This is the GEMS, aerosols, and trace gases and application product. As I explained in the introduction, GEMS will provide column amount of atmospheric aerosols and trace gases also. The trace gases means that total ozone or ozone profiles, formaldehyde and glyoxal, nitrogen dioxide, sulfur dioxide, and cloud information over here, and aerosol properties like AUD, SSA, or aerosol loading height. Synergy of hourly measurements of aerosols and trace gases from GEMS will be key to understanding highly varying air quality status comprehensively. This is the real last part of my presentation, how to access those data sets. First of all, the AHI HIMAWARI data can be available from the JAXA official homepage. The JAXA provides AHI data and images through this homepage. FTP service is available for level 1B radiance and level 2 aerosol data. And right figure is the one example of the JAXA homepage. Next, this is GOCI and AHI aerosol data generated by our Yonsei University. The specific period during the cross AQ campaign, May to June 2016, is freely available at below link, two links here. Then we can get you can check these folders in the FTP homepage about AHI and GOCI. The GOCI data is start from the March 2011 to the current, and AHI is ready for the 2016 and March this year and now. This GOCI and AHI Yonsei Aerosol data and images are also available through the FTP server operated by our group, Professor Jun Kim's group. To get this data, please contact to our group, Professor Jun Kim, or other guys in here. I wrote down the email address here. Also, after the launch of GeoComSat 2B, GEMS and GOCI 2 aerosol products are also will be also available through the Professor Jun Kim's lab. So please contact to this data in near future. For the just checking about the animation image, not for the aerosol data exactly. So then you can download this daily GOCI and AHI AUD animation figures at this Google Drive link operated by our lab. And then you can get this 10-minute temporal resolution of AHI image over the RGB image. So you can see the cloud condition and aerosol condition together, and also the 1 hour temporal resolution product of the GOCI. And GOCI and AHI, their aerosol data format is HDF4. So the Panoply program by NASA is a very useful tool to plot images. So please keep this program also. Other useful homepages. The GOCI official homepage is here by COSC kiosk. So you can see the GOCI level 1B data and other general information. You can get that information from this homepage. And the second one is the GEMS Science Team homepage operated by our group. And you can see more details and can be found with presentation files and lectures. We also have the every year GEMS Science Team meeting, and all of the materials are uploaded already, so you can check it. And our group homepage is here. So we are welcome collaboration opportunities. And last one is the reference for our GOCI, AHI, MI, and GEMS as retrieval algorithm and its application. So please find these references papers if you have some interest. Thank you for your attention.
Okay, now we are going to take question answers for this session. I will be taking question answer on behalf of Dr. Choi. He will not be able to join for this live session as he is in South Korea. So I will be answering some of the question on his behalf. Okay, great. So I have some question in front of me. I hope you can see my screen and read it here. So the first question is, are there any similar air quality satellite covering Africa or plans to have them? There is the satellite or sensor called Surveyor, which is on board on one of the Meteosat satellite by European Space Agency, which provides data over Africa. Although it is an old GOES imager type sensor and it does not have that many spectral band, so it's not as advanced as GOES or HIMAWARI sensors. In next few years, ESA will be launching a sensor called FCI, which will have similar capabilities as GOES are. Next question: how useful air quality sensor in geothermal environment, which is indicated by among other factors like high CO2, H2S, or radon gas? Can these gas concentration anomalies can be detected? Uh, so we can do CO2 from satellite. There are a number of sensors actually up in the space which can actually make measurement of CO2. But I'm not aware of any other data or methods which can do the other gases like radon. Hopefully in future, once we have this more hyperspectral instrument um, flown in geostationary orbit like TEMPO or GEMS we talked about, that they might open some opportunities to look other gases. Another question is AOD calculated with MODIS image has the same inappropriate pixel masking like GOCI, GEMS, or AHI. I am not sure what the question is here. I'm not sure what is the inappropriate pixel masking. Um, so if you can rephrase your question or if you can clarify, then I will be able to answer it. What method do you recommend to use to adjust the MODIS data for PM 2.5 for Guatemala City because there is no Aeronet platform? For converting aerosol optical depth into PM 2.5 is a we have done number of webinar series on it, and I would strongly recommend to go over some of those series. There are a number of ways in which one can convert AOD to PM 2.5, both statistical modeling and physical modeling, and depending on purpose of the calculations and how frequently you want, and if there are any ground data available or not, you can adopt different methods. So I strongly recommend look at the webinar series which has been linked here. Same thing for question number 5. Please go check our webinar series on advanced AOD PM to point foreign conversion. Question number 6. Is there any available satellite data for North African Sahara which satellite can use for air quality studies over Middle East? I already talked about the North Africa or Saharan region. Uh, there is no similar geostation satellite over that region yet, but there are polar orbiting satellite which provides data all over the world like MODIS, MICE, or VIIRS. There is Indian satellite which does cover some part of Africa and Middle East, including India, and we will cover those in week 4 presentation. Question number 7. Do you think that RGB channels or products is more useful to determine or quantify dust or aerosols? It depends on what kind of, if you're only looking for dust, then you will require channels which can actually differentiate dust from different backgrounds, aerosol sources. So for example, over Sahara where surface is very bright, looking only RGB channel may not be able to help you. So you have to have more spectral channels to separate the surface from the dust. If you're talking about in general aerosols, most often we use RGBs to do that, but we also need other channels like thermal channels, IR channels, or near IR channels to make correction for other atmospheric components such as gases, Rayleigh scatterings, um, and surface reflectance. Currently, we have PQ200 ambient particulate matter sampler with the data of hours, days, and weeks in point of the city. The most affected by vehicular fleet. When interpolating this data, I would like to adjust them with the data of MODIS. For what method could you recommend me? First of all, I'm not familiar with this specific sampler PQ200 ambient, but if you have PM data over one station and if you want to calibrate modis 1 kilometer or 10 kilometer aerosol products. You can do some statistical modeling if you're only interested at local level and not so your statistical modeling may provide good results at local station, but it also depends on many other factors, how much variability is there within the city limits, and how and what kind of topography you have, what kind of surfaces you have. Is the city is vegetated enough? So there are a lot of factors which goes into play. You will have to do some statistical modeling in order to understand the quality which you can get from the satellite. Is there any initiative to have some similar satellite program like AHI on the Caribbean? The Caribbeans are covered by US satellites, GOSR and GOES, uh, mm, and you should be able to get the data freely over Caribbean from both of these satellites. They have a similar quality as AHI, but over America and Atlantic and Pacific Ocean. Okay, another question. For the air quality management angle, is there any existing projects or effort in progress where a remote sensing air emission is directly used in models to determine the impact of sensible area or population and be adopted to other region? Is that something feasible for government agencies in countries in developing right now? There are several efforts where actually satellite-based emissions database have been derived, and they are uh, agencies like NOAA, EPA, NASA does use them into model uh, to account for emissions from various sources. For example, uh, aerosols emissions or trace gas emissions from the fires have been developed using based on the fire detection from the satellites. Dust emission factors all over the globe have been derived using satellite data again and been used by various modeling groups all around the world. NO2 emissions and SO2 emissions have been also derived using the satellite data, and various agencies have been using them. Uh, Currently, a lot of these efforts have been at the research scale. Not many agencies have adopted them in an operational sense. Some of them have done it in operational sense, but there is still room for evaluation and making understanding much understanding the satellite data, how it can be used for regulatory purposes. People are using it for monitoring purposes, but not for regulatory purposes. Is there going to be an assignment for the webinar series? No, we will not have an assignment for this webinar series. Okay, question number 13. I have always had problem with the recovery of aerosols because the city throughout the year is quite cloudy as I get few data of aerosol optical depth. What could I do? Unfortunately, no one can do anything if your city is consistent, if your city is consistently cloudy, because most of the aerosol optical data which we gathered is using visible channels or optical channels, and if there are clouds, then we cannot penetrate those to see through the clouds. You can use some lidar data like Calypso satellite, which can penetrate cloud up to some extent depending on the thickness of the cloud and optical properties, and that can provide some data, but it's very limited. Question number 14. How can the remote sensing data be used in forming government policies regarding source specific mitigation? Hmm, I'm not familiar exactly actually how you can use them, but I will give you some example where various government agencies have been using the remote sensing data. For example, US EPA and state agencies use satellite data for to submit a uh, exceptional event case studies where certain states uh, can actually use the satellite remote sensing data and show that the pollution which has been affected their particular state or city has been not originated in that state and coming from transporting from another state or another or from source far away from that state. Now that's one where people have used that. Also, based on long-term data available from the satellite, in places where we do not have any ground measurement, we can perform a long-term trend analysis and see and identify hot spots in specific countries or region where air quality has been degrading or improving, and that can be used as source of information while forming the policies. There are other ways in which people have been using the data for specific policies uh, to put in place. Okay, I think we have answered all the questions. If you have more questions, feel free to email us, and we will be able to. We will post this question answer transcripts on website, and next week we will have a speaker from India, ISRO India, and Dr. Prakash Chauhan. He will be talking about data and some of the capabilities from the Indian series of geostationary satellite called INSAT, and we will see how to access those data and some of the details of those measurements. Until then, have good night, good day, and see you next week.